Alright, so this is a typical 3-point cross. These data usually have the same format. You see 8 different things, and some of those are parentals, some are single crossovers, some are double crossovers. And the genes that we are working with are H, E, and P, and because that's the way they're listed in the question, I'll just leave them that way for now. We may have to change the order depending on what happens when we analyze the data. And so we have a triply heterozygous female is test crossed. So we don't know how that female is triply heterozygous. We just know that she is. The way I go about these is I look for the parents, or the non-crossovers, and I identify the double crossovers. The double crossovers tell me which alleles start out together. You can see that held out was by itself, and ebony and pink were together. We don't know the order, but we're going to put it in the order like this, which means E is in the middle. So we don't write H, E, and P all on one side of the line because the parentals tell us that the H started by itself and the E and P started together. But are they in the right order? Let's see what we would get if we did a double crossover. Well, actually what we want to do, we could see what we get if we get a double crossover. We could write out all possibilities of this and then do double crossovers and see what happens. But what I'm going to do instead for now is I'm going to take these double crossovers and I'm going to write out there, so it's H and P together. And if I write them in the same order, they're like this. Now, which of these had to switch sides to give us this? Well, if H switches sides, then we got H, E, and P together on one side, and that's not it. If E switches sides, we get H, E on one side and just P by itself on the other. That's not what we got. If P switches sides, then P is going to jump up here and the plus is going to go down there. Then we'll have H and P on the same side and E by itself. So that tells us that P is in the middle because that's the one that switched. So we can rewrite this. We'll write it down here with P in the middle. But we have to rewrite this. These are the double crossovers. We were just using that to figure things out. But we still know that H is by itself on one side of the line and the other guys are together on the bottom of the line, but P is in the middle. Now to calculate the distances, the distance between H and P, and I'll just spread this out a little bit so we can see what's going on. The distance between H and P is going to be a crossover right here. If it crosses over there, then H, P, and E go together, plus and plus go together. So H, P, E, and plus. Up here, H, P, E. H, P, E is this one, 106, plus, so wild type is all pluses. So we're talking 106, 104. Add in our double crossovers. Got 21 of those. Just always add those in. 10, 11, what do we got? We got 210 plus 21 is 231 over 1,000. So that is 23.1 map units. Let's write this again over here, H plus over plus PE. That's our starting thing. So this is actually what would be the answer to that. That's what our starting thing is. Our starting genotype. Thing might not be the most descriptive. And now we want to cross over here between P and E. So H and plus and E go together, plus P and plus go together. So we've got H plus E plus P plus. That's got to be these guys, because these are the only guys we got left. So these 106, 104 these are single crossovers between H and P. These are double crossovers. These are parentals. So these have to be single crossovers between P and E, because that's all we have left. But it's useful to do this and see what would happen if we got a single crossover between P and E. And so H plus E, that means it's held out in ebony together. Held out in ebony. P by itself, pink, 50 and 40. Add them together, 50 plus 40 plus 21, because we always add the double crossovers. We get 90, 111, over 1,000. So P and E is 11.1. So we have to draw that map. Getting a little crowded here. Let's move this out of the way. So this pen makes it so I have to draw really huge. I'll try to leave you some more space, or you won't have to draw as big. And on this, well, so let me just draw the map first. So we have, what did I say was in the middle? I don't know, like P's in the middle. So we've got a map between H and P and between P and E. P and E is 11.1. The other one is 23.1. So that's the map. You could write it the other way around with H over here. You just have to make sure that you have the right distance between the two different letters. And so either of these is acceptable. So we'll see a couple more of those. It just takes practice. There's several in the book. There's a few on here. Some of the ones on here might be the same as the ones in the book. And you've generated your own using the Virtual Fly Lab. So there's no shortage of 3-point crosses. I got another one on this thing later that we'll do. Alright, now got all kinds of stuff going on here. A hypothetical individual that's heterozygous for 2 genes. So this is just asking you what happens if you're heterozygous for 2 genes on various things, under various circumstances. So we don't know. So if the genes are on different chromosomes, we're going to get these kinds of gametes. 25, 25, 25, 25. Genes are in repulsion and are 20 map units apart. Repulsion means this. Now keep in mind these questions came from several different exams, so some of them are pretty similar. So these are parents. These are the recombinants. The recombinants, there's 20 map units apart, so there's 10 of each recombinant. And there would be 45%, 40% of each parental. So parentals and recombinants. If you just look at these things, you might think these are the parentals, but they're not, because we're in repulsion. Repulsion means we look like this. If they're coupled in 20 map units apart, then these are the parentals. 40, 40, 10, 10, 20 map units apart. The genes are in repulsion are 65 map units apart. Doesn't matter if they're in repulsion or not. If they're 65 map units apart, man, I gotta leave some more room. Then they're, we'll just say 1 to 1 to 1 to 1. All those things. Because the maximum they can be apart. Now you might say, wait a minute, you said the maximum they can be is 50 map units apart. Well, they can be farther apart. It's just, but when you do, it's just that you can't tell that they're farther apart. You can't tell precisely how they are. But if you map a whole bunch of genes, you can have two genes that are super far apart on the chromosome, and by mapping all the genes in the middle, you can add it up to 65 map units. But if you try to do recombination just between the two that are on the outside, it's going to come out as 50%, even though it really is 65%. So that means, so when we say 50%, that means 25 of each. And even though we don't know which of these are I guess if they started out in repulsion, then we would know that these are the parentals and these are the recombinants. And if the parents equals the recombinants, then the recombinants over the total equals 50%. Same answer here. But if there's no crossing over, then we're going to get this. These are the parents, these are the recombinants, and if there's no crossing over, what are we going to get? What we're going to get, let's say they're on this chromosome, super far apart. If we allowed crossing over, there'd be all kinds of crossing over between here, but we don't allow crossing over, so we can only get parentals, which are these. Up here we get recombinants and parentals from independent assortment. Down here it depends on crossing over. And so if we inhibit crossing over in this last one, then we only get parentals. Here we could inhibit crossing over by using males in Drosophila, for example, and we'd still get that because crossing over has nothing to do with it. Alright, this is just an X-linked one. This one I didn't mean to put on here really, because this one's too easy. We've already done just straight up X-linked mutants. But you could get an X-linked, let's see. Here, let's make this tougher. Let's say we've got two genes. We're going to take white-eyed females and mate them with, we're going to say, singed males. What does it expect? And we'll say that these are 10 map units apart on the X chromosome. So now we're going to take white females, which are wild type for singed, and we're going to cross those to singed males, but the singed males, and so we're saying that white and singed are linked because they're both X-linked, so we know they're linked. And we get plus singed over male. So this one's pretty tough the way I did it, but we're going to get white plus over plus singed. And then now let's do a test cross. So we won't do an intercross. Because as it's written, it's just a simple it's just a simple X-linked thing with one gene, and we're not going to have any more examples of those. So I thought it was an X-linked with two gene thing. So let's do a test cross. So we take this. What would be a test cross be? It would be a white singed male. So down here we'd get white plus singed plus and white singed. And the males and females would have the same results. All right, these would be the parents. These would be recombinants. 10 map units apart. 45, 45, 5, 5. Just looks a little bit different when you do the cross with two X-linked genes. And you could also do this with you could do a 3-point cross with X-linked genes if you wanted to. Here's another one. pretty similar to all these other guys. This is super easy. Well, I don't know how easy it is. They all look, so this looks like about 300, 300, 200, 200. Well, this might have been on our quiz. So that looks like these are the more, these are less. So we've got 400 over 1,000 equals 40% equals 40 map units. So this is just saying that we are rejecting the hypothesis that there's independent assortment. If we've got 1,000, we would expect independent assortment to be 250, 250, 250, 250. And then if we do a chi-square on this, we get this p-value. And so we reject that it's 250, 250, 250, 250. So what's the genotype of the parents that gave rise to this heterozygous individual? Well, the parents were in repulsion. So that's their genotype. Considering the same two genes as above, an AABB individual is this, then you get your double heterozygote. What do you get? Parents, recombinants are a little bit different. These are your parents, so you get, what are we getting? 30, right? 30, 30, 20, 20%. Alright, easy enough. Some more chromosome drawing. Again, I cobbled this together from a couple different exams. So, like I said, practice, do the same thing more than once. Alright, below are four diagrams, each representing a pair of homologous chromosomes, indicate the positions of the alleles. You decide. Alright, well, coupling is easier than repulsion, so let's couple them up. Maybe I'll change it on the next one. Alright, and then A, indicate the types of gametes. No crossing over. Only those. Yeah, we'll keep them the same. Single crossover. And then get a little colorful here. We'll get these. We'll get little a and big B going together. Big A and little b going together. Little a and little b going together. Spread them out a little bit. Wait, it says single crossover again. Well, that's no fun. So let's do double. AB. Now we get one of these guys. Big A and big B together again. Get little a crosses up, comes back down, gets little b. So, all parentals. These guys have 50-50 parents to recombinants, and these are all parentals. And there you have it. Oh, look at that. Another, oh, dikeet black and yellow. Alright. Dikeet black and yellow. Let's see. Alright, so you guys, so this is, I just made up some numbers I think here, but since you guys have been playing around with Virtual Fly Lab, you might remember that dikeet is, well, you probably don't remember, but dikeet's not X-linked and black, you know, I don't know. These aren't really all in the same chromosome, but these are just numbers that are made up with some kind of cross. But anytime you see this, you've got your three things mapped together, and so you always get the same characteristic set of 8 things, where these are the parents, these are the doubles, then these will be the singles between 2 genes, and these will be the singles between 2 other genes. So let's figure out what's going on here. I don't even think you have to write out all of the genotypes and everything ahead of time, if you just say D, B, and Y is going to be our order because of this, just the ones that are all written together. But this tells us that D is on one side, B and Y are on the other side. And they always get a plus, the wild type going opposite them. Alright, so what do the double crossovers look like? The double crossovers are these guys, D and W. We're going to double crossover. Now we're going to get D and W, D and Y on one side. And I guess just B on the other side still. So which guys switch sides? To go this way, it looks like yellow switch sides, because now yellow is up here with D. It seems like the last couple of examples it's been the third one that's jumped up. It's not always that way. That tells us that Y is in the middle. So we're just going to rewrite this. We know that this is still our original arrangement with D on one side, B and W on the other. So D's by itself. But this just told us that Y is actually in the middle. So now we'll put Y in the middle, B over here, plus. Then we get rid of all that, because that was just to figure out which one was in the middle. Now we want to think about single crossovers. If we get a single crossover between D and Y, it's going to be D, then YB. It's going to be plus, plus, plus. So that's got to be one of our single crossovers up here. That's these guys. So this is a single crossover between D and Y. Well, this must make these guys, this crossover is between Y and, what's the other one? B. Alright, so these guys are 45 plus 44, add in our double crossovers, equals something. I'm going to try my new calculator. Just got a new calculator from the dollar store for $2. So, hard to beat that. 130 over 1860. 6.98. We're going to give it a 7. 7%. Alright, the other guys up here, between Y and B, are going to be 206. So they're farther apart, we can tell that. Plus 41, have to always add in the double crossovers. 206 plus 204 plus 41, 451 over 1860. 1901. I think I just added them to 1860. 451 divided by 1860. That's what you get for $2. 24.2. So that's our distance. So we'll just put our map up here. So we've got, what did we say was in the middle? Y is in the middle. So we're going to go D to Y. And which one's longer? Y to B is longer. So we'll draw it a little bit longer. So it's a little hard to keep track of all this stuff. So this one, it's nice if you have different colors. So dy is 7%. And Y to B is 24.2%. So, kind of on the complicated side, but again, take some practice, figure out your own way to do it. Now, this is my infamous problem that I often put on there. Good news is I'm giving you this ahead of time. Bad news means I have to think of something else kind of creative. But this is one that makes people think, and it rewards the people that are paying most attention. Alrighty, and I try to, each time I give this problem, I give more information. Alright, so here we go. We got some flies. Autosomal recessive. Here we got bright red and brown. Together, they're white. So this does have a little bit of epistasis involved. So we've got, if we're homozygous mutant for both of them, we're white. So all of these things are going to be the same deal. We're going to have big B, little b, big S, little s, and we're going to do a test cross. But we're going to switch up whether this is a male or a female. And let's see if I told you that on this one. Now, sometimes I'll tell you just because people could never remember. But remember, what's the big deal with males? No crossing over in males. Also, what's important is this on the X chromosome. Geez, I'm saying males and females a lot. That makes me think I want to put in some X and Y chromosomes. But why would I do that? They're autosomal recessive. That means they're not on the X chromosome. You got to read these questions. That's one of the reasons we give them to you this way. It gives you good practice. Good practice for the MCAT. Good practice if you want to be a lawyer. You got to read things carefully. All right. So in each of these several crosses, what's going on? Heterozygous female is test crossed. So if they're on different chromosomes, we're going to get. So we're doing a test cross. We'll get big B, big S, big B, little s, big B, and little s, little b. Alright, so if we have big B, big S, that's wild type. This is scarlet. Oh, these are the same thing. So these got to be, switch things around. So we got big B, big S. Big B, big S, and then we're going to have little b. Little b, big S, little b, little s. So wild type, scarlet, brown and scarlet, but they're white. And they're going to be 1 to 1 to 1 to 1. If they're heterozygous male is test cross, so that's if a female was test cross. If a male was test cross, what would we get? Well, let's see here. How do we set this up? So brown is mated with scarlet to start off. So that means that these guys were the parentals because we crossed brown to scarlet. So now we'll get 50-50. If they're 20 map units apart, so we're going to continue to get these things. And these are going to be wild type. These are going to be scarlet. These are going to be brown. These are going to be white. Because we started out this way, we crossed a brown to a bright red, so that's a brown to a scarlet. We know that our parentals are always still going to be the same. So these are parentals. These are recombinants. If we use a female, and they're 20 map units apart, then we'll get 40 of our parentals, 10 of our recombinants. But if we used a male, we're going to get 50-50. 0, 0, parentals, recombinants. So this problem is really just to really illustrate where the parentals and recombinants come from. Oops, I messed this one up. I got a little ahead of myself. Different chromosomes. What's that mean? No crossing over. So they're the same. I'm not going to re-record this. I'm just going to let you guys deal with that bit of ambiguity. I try to do these kind of quickly sometimes. It's kind of a trade-off between being super careful and taking forever. So different chromosomes, then they're going to be the same no matter what, because crossing over is irrelevant. This guy, we've got 20 map units apart. If we use a female, we'll see that 20 percent recombination. Males, we won't get recombination because they're linked now and we don't get crossing over. If they're greater than 50 map units, a female is test cross, we'll get 1 to 1 to 1 to 1. But if they're on the same chromosome and they're greater than 50, so it looks like independent assortment if there's crossing over. But here we'll get 50-50, and we're going to get 50-50 of the parentals, and the parentals are scarlet and brown. There's that one. Alright, so that's it. So I got another space here, so let's just do that again. Brown, cross to scarlet. We got a heterozygote that's viewed for brown. So this one is brown, but wild type for scarlet. So we'll give it a big S. And then from this chromosome, we're going to get a little s, because this one's little s, little s. This one's little b, little b. But big S, and big B, big B. So, in every cross, that'll be our parental. And these will be our recombinants. If recombination is greater than 50 map units, so let's see here. So if we have independent assortment, we'll do females and males. So we're talking about if this individual is a female or a male, and then we're going to test cross it to something like that. If we have independent assortment, we'll always get 1 to 1 to 1 to 1. If we've got 20 map units, we've got a female and a male. These are our parentals, 20 map units. Female will give us 20 map units, that's 10 recombinants each, 40-40. But the male will give us all recombinants, because these are recombinants now. If they're greater than 50 map units, let's make another color. Greater than 50, and we use a female, 1, 1, 1, 1, or 25, 25, 25, 25. And males, even if it's greater than 50 map units, but they're on the same chromosome, greater than 50, but on the same chromosome, then you get this. It's because, and the main difference here is we're comparing this. It's the same cross, but we're using, if we use here, there's independent assortment, so crossing over has nothing to do with it, and we get 1 to 1 to 1 to 1.